Now we would like to start our next chapter, and the name given by me is the chapter 2B. Our previous chapter was introduction of the barrage, and that was chapter 2A, and now this is chapter 2B, because we are discussing the about barrage, but in a different way. The name of this chapter is surface flow considerations in barrage design. We know very well that barrages are provided over alluvial foundations. I think you have an idea. Barrages are provided on alluvial beds. These are not provided over the rocks or rocky foundations. As barrages are provided on the alluvial beds, so a barrage structure must be safe for the surface flow conditions as well as subsurface flow conditions. So water seeps in the alluvial beds like sand or silt. Under the barrage there is sand or silt. Okay, and the water also moves under the barrage. So the barrage should be safe for these both considerations, that is the surface flow or overflow consideration and subsurface flow consideration. But this chapter only deals with the surface flow considerations. Surface flow is also known as overflow, okay, consideration. Now we have to take care of these things in case of surface flow considerations. First of all, estimation of the design flood. What should be the value of the flood on which the hydraulic structure or the barrage is to be designed. Number two, how we can design or compute the length of the barrage. Okay. The secondly, we must understand the retrogression phenomena, which is a temporary phenomena, and but what it is very important in the design of the barrage for surface flow, considering surface flow. The next phenomena is accretion, and we must understand what is accretion in case of a barrage. And then the barrage profile. So we should be able to design the barrage profile. Once we say the design of barrage profile, it means we must be able to design the level of the upstream concrete flow. And then how much should be the length of the upstream concrete flow. The next is what should be the slope of the upstream glacis. Then we must design the level of the crest of the barrage. Then how the design of downstream glacis. And then we must be able to fix the level of the downstream concrete floor and also the length of the concrete flow. So these are the items which we must design by considering surface flow considerations. Okay, but now we will go to one by one. First of all, the design flood estimation, how we can basically design flood of a hydraulic structure or barrage. It depends on these three major factors. How much is the life of the structure? Means the life of the barrage. What is expected life of barrage? What would be the capital investment or cost it requires? And what are its economic importance? Okay, so based on these all factors, we take certain value of the design flood. Usually a design flood for the barrage is taken as it given in the book is 50 to 100 year return period. But you know, now more emphasis is given on the 100 year return period flood. So nowadays a barrage must be designed by considering at least 100 years return period flood. So how we can find 100-year return period flood? Yes, somebody would describe it. What is the procedure to compute 100-year return period flood? Yeah, by applying flood frequency analysis approach. So by flood frequency analysis, we can find 100-year return period flood, or we can find any return period flood. And you know, for doing this, for finding this design flood, what data do we require? You know, the maximum instantaneous discharges of each year. So highest value of the flood of each year that we require. And then we have to carry out the flood frequency analysis. So you have already done flood frequency analysis in your hydrology, engineering hydrology subject. Okay. So from there, we can find that what is the value of 100-year return period flood. On that flood, we will design a barrage. Is it clear?
Yes, sir.
Now the second is the barrage length. Barrage length means width of the barrage, basically. The width of the waterway, how much we should take the barrage length. As I mentioned you earlier, that the width of the river is a function of discharge. Width of the river is a function of? Kya bhai?
Function of discharge.
This B, let's say B is the width of the river. We know that this is a function of Q. है ना? When the discharge would be more, the width of the river would be more. Even on 100-year return period flood, the width would be too much. And the barrage waterway, we cannot provide up to that. Though we can provide the marginal bonds up to that extent. Okay, but not the main barrage part, which are the weirs, which are the main base and the undersluice base. Their width we keep shorter. Okay, and for this purpose we use Lacey's equation for wetted perimeter. So according to Lacey, wetted perimeter is 2.67 root of discharge. This is an English system, and in System International 4.75 root of discharge. So wetted perimeter of a channel is a function of what? Kiska function hai?
Discharge.
Function of discharge. And you know, this equation of Lacey, it has been tested on many rivers and only many artificial channels, and its performance remained good. So finally, how the length of the barrage we can compute using this equation, which says that length of the barrage L, that is equal to LLC, Lacey's looseness coefficient, and this is the wetted perimeter, which is given by the Lacey, and this is 2.67 root of Q in English system, and it is 4.75 root of Q in SI. And this Lacey's looseness coefficient, its value ranges from 1.2 to 1.8. It means whatever is the wetted perimeter value, we further increase it either by 20%, from 20 to 80%, This is further increase. This is the standard practice to compute the length of the barrage. Okay. And here, you know, the wetted perimeter we are saying is very close to wetted perimeter is approximately equal to width of the river. Is it true, Ji? B.
Yes,
Why?
sir. So very
Yes, sir.
Because this is the river in case of alluvial plains. Very, very large widths and depth is very small. So how you will compute wetted perimeter? Only this depth plus this depth plus this width. So this width is very large. So this is, we can ignore the depths. So we can say that wetted perimeter is approximately equal to width of the channel or barrage or river. So this is how we have to compute the length of barrage. Shall we move ahead? So length of barrage should be Lacey's looseness coefficient into wetted perimeter given by Lacey. Now retrogression. What is retrogression? You know, retrogression is a temporary phenomenon. Temporary. What do you mean by temporary? To explain retrogression, we are here. What is this? This is the main barrage portion. Which one is the upstream side? This is the upstream side. Yes, and this is the downstream side. So the flow of water is in this direction. And this is the upstream concrete floor. This is the upstream glacis. This is the crest of the weir. This is the downstream glacis. And this is the downstream flow. Okay. And we want to study the retrogression. What is retrogression? You know, if the gates are closed or even not closed, now this would be the, profile, how the water will flow. This is the water level in the upstream side. Due to the construction of this weir, you know, this whole weir. Now, what has happened on the upstream side to the depth of flow? Is it same or increased?
So it will increase depth of
on the
flow.
same value of the discharge. Okay, discharge is same, but the depth of flow has increased. Once the depth is increased, what would happen to the velocity of flow here? Velocity ko kya hoga? That should reduce. Well, when the velocity will reduce, due to that the sediments here, they will deposit on the upstream side. So here you will find many sediments. This is temporary phenomena. Once, just after the construction of the barrage, it happens. And then the water which moves over the weir, how much sediments it has? It has less sediments. And when it passes here, this is the bed of the river. Okay, this is the natural river bed. And this water contains very less silt. And then we call this water as the silt thirsty water because it has more energy. And then what it does, it picks silt from the downstream river bed. Due to that, what happens? The downstream river bed goes down like this. And This phenomena is called as a retrogression. So what is retrogression? It is the lowering of downstream river bed due to flowing of relatively less silt water. And so this much is the retrogression. This was the original bed, and this is called as retrogression. Retrogression. Okay. Now you go back here and you will read from here. It's a temporary phenomenon. When it starts, which occurs after construction of weir or barrage in a river flowing through alluvial soil. Is it okay? As on upstream side, the depth of flow increases, the velocity of flow should decrease, resulting there would be deposition of sediments on upstream side. So therefore, the water overflowing the barrage has less silt, as we have seen earlier, picks up silt from the downstream bed. So this results in lowering the downstream river bed for few miles. This retrogression takes place for few miles. This is known as retrogression. You know, it may occur for few years, maybe for 2, 3, 4, 5 years. And the bed levels often recover their previous level. Would you follow it? And you know, after certain times, the bed level may recover like that, or maybe 90% or 80% it recovers after certain years. Values of the retrogression may vary from 2 to 8.5 feet in Pakistan. So this retrogression, how much is this value, which is being observed in Pakistan? 2 feet to 8.5 feet. There is a lowering of the river bed level from downstream side. Retrogress level is important, very important, while fixing the downstream level to ensure the formation of hydraulic jump at the toe of the downstream glacis. Actually, the formation of jump is a function of downstream water level. Okay, if you see here, if the downstream riverbed is retrogressed, then the depth of flow here is reduced. And this hydraulic jump which was forming here, it may form maybe here or even on the downstream floor. So when it will form downstream floor, it is unsafe. It prolongs the turbulence here, and then downstream riverbed is further eroded, and which can further damage the barrage. Therefore, its formation has to be checked for retrogress level, for normal level, and for accreted level. And so we always want to create hydraulic jump on the lower third of the glacis. Okay, downstream glacis. Why the hydraulic jump is being created? What is the main purpose?
Sir, the main purpose is to dissipate the energy of water.
Yeah, air cooler
Yes.
ban.
Yeah, sir.
To dissipate the destructive energy of water. Okay. And so retrogress levels are more critical in deciding downstream flow levels. Why more critical? Can anybody tell me? So this is the normal level, normal riverbed level. And this is the retrogressed riverbed level. Why retrogressed riverbed level is more important for designing of the barrage? Why? What we want that the hydraulic jump should form on the downstream glacis, which is this one. Okay. And suppose if we have checked it on normal level, normal riverbed level, let's say hydraulic jump was forming from here, from this section. But after a few years, maybe 2-3 years, retrogression took place and the riverbed level has gone down. Now the depth of flow here reduces, and this hydraulic jump instead of this location may form at this location. When the hydraulic jump start forming at this location, the turbulence there would be more turbulence which will reach to this downstream riverbed and it further erodes. So that is not safe. So if we assume that this much retrogression has occurred, and on this retrogression, or if our hydraulic jump is forming here on the lower third of the downstream glacis, then after retrogression, when there would be accretion and the riverbed level will come to their original position or close to original position, then this hydraulic jump will further move up, which is safe. So it means retrogressed levels are the most critical for the design of the barrage. All right, Jay? So that is the retrogression. And how much the retrogression is possible? From
2 to 8. 2 to 8 feet.
8.5 feet. Retrogression is possible. That takes place in the early maybe 2 to 4 years of the construction of the barrage. Why we call it as a temporary phenomena? Why we call it as temporary phenomena, retrogression?
Sir, because after a few years, there is a reversal of this phenomenon, which is called retrogression.
Yes, because after a few years, there may be accretion process starts, and then the riverbed levels, they may recover their original levels.
So it will compensate whatever happened.
Yeah, original level. Now we have to discuss the accretion. What is accretion? Accretion is the reverse of the retrogression. Reverse of the retrogression, and normally occurs after the retrogression cycle is completed. So in retrogression cycle completion, maybe it may take 3 years, 4 years. Once it is completed, then the next cycle starts, that is accretion cycle. Okay. So by the way, why it takes place? Previously, there was retrogression was taking place. And then after retrogression, why the accretion has started? Can somebody will let me know? Can explain this phenomena? Where is that our diagram? Here. Okay, suppose the retrogression took place. Maybe after 3 years, the cycle has completed, and now the riverbed has gone down, and this much is the amount of retrogression took place. What happened on the upstream side? There was a lot of sediments deposited on the right side. Maybe its bed has risen or has rised. Now, when the bed will rise, and this is our pond level, which is fixed, we cannot go beyond the pond level. ऐसा ही है भाई?
Yes, sir.
Yes, sir.
Okay. And now what happened to the depth of flow for the same discharge? अब क्या हुआ depth of flow को? Due to 2 to 2 years sediment deposition, it is reduced.
Yes,
once it is reduced, what will happen to the velocity of flow?
increase हो जाएगी.
That has to increase. Now, once the velocity of flow is increased, it will pick sediments from here, from the upstream side, and it will carry with it. When it will reach here, what about the depth of flow here? Is more. And what will happen here to the velocity of flow? That has to reduce. Then the sediment which is carries will be deposited here on the downstream river bed. And this process is called as accretion. Now, the deposited sediments on the left side or on the upstream side of the weir, those will be transported here and will be deposited here. And this process is accretion. Accretion means recovery of the retrogressed river bed level. That is accretion. And now I think you understood why accretion takes place, why the accretion cycle starts.
Sir?
जी भाई.
Sir, ये accretion phenomena पहले नहीं हो सकता retrogression?
जी. क्यों होगा पहले यार? देखो.
सर शुरू में वो स्कार कर रहा है, डेप्थ डिक्रीज हो रहा है, फिर उसके बाद वो दोबारा फिलअप हो रहा है. तो अगर पहले फिलअप हो,
नहीं पहले क्यों फिलअप हो जाए मुझे बताएं.
क्योंकि सर उधर भी डेप्थ फ्लो ज्यादा होगा.
No, the depth of flow on upstream you increased, you disturbed the river regime. River चल रही थी पहले, उसकी depth शायद इतनी हो, है ना? On that discharge, on this value of the discharge, this was the depth of the river. You made this structure in the river. You disturbed its normal flow. And what happened? The depth of flow on the upstream side was increased. Due to that, sedimentation is must on the upstream side. So as there is a less silt water or the silt thrusty water is moving on the downstream side, it has to pick the silt from downstream side. So the accretion cannot take place earlier.
Okay, sir.
ठीक है?
Okay.
Where we were, accretion, है ना? So what is its significance? Its significance in the design is much less than as compared to the retrogression. Retrogression is very important. Accreted levels are normal levels. They are not that much important. Okay. If I have designed a barrage and if it is safe on retrogressed levels, it is automatically safe on the accreted levels or on the normal level, because those are higher and the jump will move up. So there it is safe, because the higher downstream water level tend to push the hydraulic jump to the glacis, making it more safe. Therefore, the hydraulic jump formation calculations, which are based on the retrogressed levels, will always be safe for accreted and normal levels. Okay. So that is the significance of retrogression. Accretion has not that much significance, but we wanted to understand this phenomena, that after retrogression cycle, when it is completed, then accretion cycle starts. But within that 3-4 years, if we have not designed our barrage, considering that retrogression in these years, our barrage may fail. Okay. Now this we've already discussed, and now comes the barrage profile. The first thing, the crest level, how we have to fix the crest level. This one, how we have to find this level, crest level of the barrage. क्योंकि कैसे मालूम करना है? What should be the approach? What should be the approach to find this crest level? क्या होनी चाहिए? You know, we design this barrage on a certain value of flood.
Our crest.
Gigi, please. Yes, please. Okay.
Yes, sir, our crest level should be high enough to cater the.
No, your voice is not clear. Anyway, okay, Ji, we want to fix this crest. Where we should fix this crest? Level of the crest. How much it should be above it? Do we know the pond level? What is this level? Where do we fix the upstream level of the barrage? This is called as pond level, PL. So this level is pond level. By the way, how do we fix pond level? Pond level कैसे fix करना है? क्यों भी barrage का pond level? It should be where? We have to see that on what is the highest flood level, what is the flood level on this designed flood. Okay, let's say design flood पे ये level आता है, for design flood, and then we have to see that how much the water will rise due to provision of this weir and due to damming action. That rise of water level is called as, on upstream side, what it is called? Kya bhai? Due to the weir provision, the water level will rise on upstream side. What it is called?
Flux, sir.
Afflux. Afflux. Yes, good. So it means we know the depth of flow at the design flood and we know the afflux. So if we will add them, we can find the pond level. Okay. So, okay, we can fix that. This is the pond level. Or even we can go further up. All right. If to increase the command of the barrage. So, but at least how much we should go up? Whatever is its stage on the design flood plus afflux, we have to add, and we can find the pond level. Now, then, if we know the pond level, then how we can fix this crest of the weir of the barrage? कैसे fix करना है भाई? Let's say this is small h. What is small h? यहाँ से यहाँ तक. What is small h? I think you have performed experiment on rectangular notch and V notch, and you know what is small h. Small h is the head over the crest of the notch or weir. So this small h is the head over the crest of the weir. Okay. And we know the design discharge Q. That we know. Please mute your mics. We know the Q. Design discharge. So on design discharge, can't we easily compute what would be the value of the H, which is the head over the crest of the weir? Can we easily compute? Yes. By which formula? By discharge formula of the weir or discharge formula of the notch. If it is notch, this is not notch, this is weir. Huh? And you know, for notch, what was the formula for actual discharge? CD times, for rectangular notch, 2/3 root of 2g h raised to 3/2. Where that h is this h. ऐसे ही है भाई. Or h was the total head. H was the total head. ऐसे ही था ना भाई. ये वाला हेड था H, कैपिटल H. So it means I can find H, and if I have the value of small h, then how I can fix the level of the crest? I know the pond level. So pond level minus H would be the level of the crest of the weir. So this is how you can fix the crest level. So we have to compute the velocity of approach. How we can compute the velocity of approach? Q over Y R R. R is the cover depth. So therefore, velocity head would be V square over 2G. This is approach velocity head. And this would fix the upstream energy line. How much is the specific energy E1 on upstream side? Y1 plus V1 square over 2G. Okay. And we know the equation of discharge for free flow. Discharge is CLH raised to 3 by 2, where H is the total head, which we have seen here. So this total head, small h, is just the depth of flow, or head over the crest of weir without kinetic head. And this is the equation for submerged weir or submerged flow. Discharge is C dash LH raised to 3 by 2. And total head is H plus capital H is small h plus V square over 2G. This is the approach velocity head. And H is the head over the crest of the weir. This we used to measure even in the experiment in lab. The value of the C is the coefficient of discharge free flow is varies from 3.1 to 3.8 in English system. And the C dash is the coefficient of discharge for submerged flow. And for that, we have to use Gibson's curve, which is this one, Gibson's curve. Before going to Gibson's curve, you must know the difference between free flow and submerged flow. What is the difference? क्यों भाई? कोई फर्क है free flow में और submerged flow?
तो submerged flow pressurized होते हैं?
No. Both they are open channel flow. Okay, please recall that rectangular notch experiment. कोई आ रहा है ज़हन में? That was a sharpest rectangular notch, and you know when the water was passing over the notch, तो फिर क्या हो रहा था downstream पे? A nappe was forming. nappe form हो रहा था?
Yes sir.
और वो वाटर क्या टच कर रहा था डाउनस्ट्रीम पे? नहीं कर रहा था. What about here? In case of a weir, तो क्या ये free flow कर रहे हैं? Is it flowing free or touching with the downstream glasses?
So it is touching the downstream.
It is touching. So means this type of the flow is submerged flow, and that was the free flow. And if it is submerged flow, then the C dash coefficient of discharge for submerged flow we can find from Gibson curve. So this is the Gibson's curve, and the variable on y-axis is h over E is the total energy, and the small h is head over the crest of the weir, and C dash over C. If we know the C and this for this value, we can go here and we can find the value of this ratio C dash over C. We know the C, so we can find C dash. Okay. I'm sorry, these are not readable, but in the book you can read it. Huh? So I have shortened it. Is it clear, Jay? So C dash you can find, and then you will use this equation. आपने ये वाली equation use करनी है, and which is for submerged weir, and from here. then you have the value from this equation. What you will compute? You will compute this H. Because you know the discharge, you know the C dash, you know the L, so H you can compute. And this you know this approach velocity, and then you can compute small h.
Excuse me,
And
sir.
once, yes.
सर हम अप्रोच वेलोसिटी के लिए हम स्कावर डेप्थ को क्यों यूज कर रहे हैं? सिग्निफिकेंस क्या है उसकी? स्कावर डेप्थ की?
Yeah, this is very good question. Actually, स्कावर डेप्थ हम कहाँ मालूम कर रहे हैं? यहाँ पर कर रहे हैं ना?
जैसे अपस्ट्रीम
पे. Because velocity of approach is on that side. Actually, this is the depth of flow, so we should use this depth, है ना?
Yes, sir.
But you know, as we do not have any depth, तो scour depth जहाँ तक scour होगी. So this is the value of R given by the Lacy. So instead of using this depth Q over Y, we say compute Q over R. So because this is the, ये नीचे कौन सा मटेरियल है? Alluvial है, and the water is also flowing over that. This is the main reason, and that's why we compute the this velocity of approach velocity of flow as Q over R. ठीक हो गया? इधर से हम. Okay. So we can easily find the H. और ये H over E ये क्या है? This is called as modular ratio. Okay. और ये वाला कहलाता है रिडक्शन फैक्टर. ओके. एनीवे, तो ये जो H हमने निकाल लिया, तो ये सो हाउ वी कैन फाइंड द क्रेस्ट लेवल? पॉन्ड लेवल माइनस H. एंड स्मॉल h कैसे निकालना है? कैपिटल H माइनस v स्क्वायर ओवर 2g. एंड देन इन दिस वे वी कैन फिक्स द क्रेस्ट लेवल ऑफ ए Weir. इज इट इजी? नाउ हाउ वी कैन फाइंड क्रेस्ट विड्थ? तो विड्थ कितनी होनी चाहिए क्रेस्ट की? This one. What should be the width the crest? तो यहाँ पे कौन सी चीज ने सीट करना है? The gate has to rest here. है ना? गेट आएगा ना इधर. तो कितनी होनी चाहिए width इसकी? The crest width should be such that it can seat the gate. Normally, a width of 1.5 to 2.5 meter should be adequate. ठीक हो गया जी? Now we would like to solve a numerical on the how to fix the crest level of the Weir. So find the crest level. Q max is given, high flood level is given, length of the Weir is given, and the value of F given, and the C dash is given. This is the coefficient of discharge for submerged flow, and so here compute first of all the small q, which is capital Q over L, so it is 5 cubic meter per second per meter. Then compute its cover depth, 1.35 Q square over F of power 1 over 3, and this is we are using System International, so answer is in meters and 8.4 meter. Compute the velocity of approach, that is the Q over R. One more reason of using R at the initial stage, we don't know the exact depth of flow. So that's why we use R as well. And that is 0.59 meter per second. Compute then approach velocity head, v square over 2g, that is, let's say, coming 0.92 meter. Now using discharge formula over broad crested Weir for submerged conditions. So Q is equal to C dash L H power 3 by 2. Putting these values, only the H is unknown, and we have determined H, which is 1.822 meter. And we know that this total head is equal to the head over the crest plus the velocity head. And as we know the velocity head, we have already computed, so we can compute the H, which is the head over the crest of the Weir. Now the crest, level, how that should be equal to the pond level minus h. So this was the pond level given 100 and this is 1.63. So the crest level is 98.37 meter. This is how we can solve this problem of fixing the crest level of a barrage, weir of the barrage. Is that okay?
क्वेश्चन था
जी
सर, फर्स्ट ऑफ ऑल इसमें कैलकुलेशंस में क्रेस्ट लेवल को फिक्स करने के लिए हमने इस चीज़ को कहाँ मेक श्योर किया है कि हमारा फ्लो अबव द क्रेस्ट क्रिटिकल फ्लो होगा या मे बी सब क्रिटिकल वाईसी को अप्रोच करेगा आपकी डेप्थ ऑफ फ्लो?
No, you know, you have already checked that. You know the critical depth, the value of the critical depth for that design discharge. That you have already computed. You know the value of the YC. Weir height you have selected in such a way that it is more than the hump height. It is causing damming action. It is more than the YC. समझ आइए बात है ना?
यस सर.
ओके, तो वो हमने पहले ही कर लिया है. और देखो ना, जो 100 ईयर रिटर्न पीरियड जो फ्लड का लेवल है प्लस वो जो उसमें एफ्लक्स ले लिया है, तो एफ्लक्स वाई वी हैव टेकन बिकॉज अगर तो ये वियर की हाइट कम होगी एज द क्रिटिकल हार्म हाइट, तो फिर एफ्लक्स पैदा नहीं होगा.
यस सर.
That we have studied in hydraulic engineering subject very clearly. If we will provide a hump, तो क्या change आती है in the water surface profile? Only the locally water surface profile goes down. बस, है ना?
Yes, sir.
अगर सब critical flow है. So no damming action takes place. No efflux takes place on the upstream side. But when over hump height is greater than the critical hump height, then efflux or damming action takes place on upstream side. So I think we should stop here because you might have the next lectures, and inshallah we will continue this chapter, and it's very interesting chapter relating with the design of the barrage. Now I would like to take your attendance. It is taken, and okay ji, if I think thank you very much for your presence and patience. Okay, Allah Hafiz.
Thank you sir. Allah Hafiz.
Allah Hafiz, sir.